sketching inverse trigonometric functions. So we're going to start off looking at y equals inverse sine of x. And in order for us to sketch this, we'll write down its domain and range. So its domain, which is just a range of y equals sine x, and we get the domain is -1 to 1. And our range we had to limit to make it a function, and that was from minus pi on 2 to pi on 2. So let's go ahead and just sketch out y equals inverse sine of x. So in doing this, we know it's going from -1 to 1 and minus pi on 2 to pi on 2. And starts off here and it's doing something like that. Remember, this is a reflection about y equals x of y equals sine x. But what happens when the function itself is varied a little bit? So let's have a look at y equals inverse sine of 2x. What does having a 2 there do? Well, having a 2 there affects the domain because it's related to x. So what we can do is we can actually sub in. So if this is ever changed, we can sub that into our domain and see what happens. So if we do that, we get 2x is between -1 and 1. And then dividing the 2 out, we know that x has to be between -1/2 and 1/2. So sketching this function out, so nothing would happen to the range here. So sketching this out, we know we're going from -1/2 to 1/2, and it's the same range, and we'd end up with something like this for y equals inverse sine of 2x. What about y equals the inverse sine of x over 3? Well, again, the domain is being affected here. So a nice way to do it is to sub that into our x for the domain. So we know x on 3 needs to be between -1 and 1. Multiply everything out by 3. So we know x is between -3 and 3. And this is going to help us sketch out this function. So we've got -3 to 3 this time. And the range isn't affected again. And we're going to get something like this for this sketch. Finally, let's look at y equals 2 multiplied by inverse sine of x. Now, this time we're not changing the domain at all because the domains, we still just have 1x here, but the whole function is being multiplied by y. So what you want to do here is, if we're multiplying all of the inverse sine of x by 2, you would just want to do the same thing to your range. So our range is normally from -pi on 2 to pi on 2, but we know now we want to multiply everything in our range by 2 because we want it to make it look similar. So we'll times everything by 2, and we get -pi is between 2y and pi. So 2y is between -pi and pi. And this gives us our new range for this function. So we know we're going from pi all the way down to -pi. But it's still between -1 and 1 because we haven't changed the domain. And we get something like this for this function. All right, so let's have a look at inverse cos. So we got y equals inverse cos x, and let's write down its domain and range. So the domain, again, is the range of y equals cos x, which is -1 to 1. And the range for inverse cos is from 0 to pi. So we're going to go ahead and sketch this out. Go from -1 to 1, and we know this is going to look something like this. Cutting through pi on 2 there. But what happens again when we change values in here that's going to affect the domain, or multiply this whole function which will affect the range? Let's have a look at another example. So we've got, let's have a look at y equals the inverse cos of x on 2. Again, this is affecting the domain, so all we're going to do is sub that value in for x inside our domain, and then get x by itself. So we'll times everything by 2. And this tells us now that x needs to be between -2 and 2. And we haven't affected the range, so we're still going to have that same range. So we're still going to go through pi on 2 there, but we're going to stretch out and go over there. And finally, let's look at y equals 3 times the inverse cos of x. And here we're timesing every value in our range by 3. So all we want to do is we want to get our range, and we want to times every value here by 3 to make it look like 3y. And we'll get that 3y needs to be between 0 and 3 pi. But again, we haven't affected the domain here, so it'll still be between -1 and 1. So we need to go all the way up to 3 pi now. And the halfway point will be 3 pi on 2. And starting from 1 and ending at -1, 3 pi. With some values, let's look at some different sketches for inverse tan. So we have y equals inverse tan of x, and let's note down its domain. So x actually belongs to the set of all real numbers, but y not equal to, y is between -pi on 2 and pi on 2. And if we were to sketch this one out, so we need to mark in some asymptotes for -pi on 2 and pi on 2 because it's not equal to it. So the asymptote's at pi on 2 and -pi on 2. And then our inverse tan function is going to look like this. Let's have a look at just a couple of examples. So if we have y equals inverse tan of 2x, it's going to happen here. So all that's going to happen here is that, remember, this domain was all x belongs to a set of all real numbers, so changing the domain here is not necessarily going to do much in terms of shifting the graph, but it's going to make it a little bit steeper. So we're going to have something like this. Something like this for inverse tan of 2x. But let's have a look at another example. Y equals 2 times the inverse tan of x. This time our range, we're multiplying everything by 2, so we can do what we did before. So we take our range, we times everything by 2 to make it look like 2 times the range, and we get minus pi and pi for that range, which means we have new asymptotes, and pi and minus pi. And our y equals 2 times the inverse tan of x here is going to look something like this.